Yo, hey guys, welcome. Yeah, so I wanted to show you how to do the Laplace transform for the two functions t times sine at and then t times cosine at. And I realized that I should first teach you about a property of Laplace transforms that's going to save you a lot of time when you're finding the transform of these two functions. And so let's talk about that property. To start, remember that for any function f of t, L of f of t, the transform for f of t that is equal to the integral from 0 to infinity of e to the negative st times f of t and then times dt, right? And we also called this integral capital F of s. So let me rewrite again. Capital F of s, the transform, is equal to the integral from 0 to infinity e to the negative st times f of t dt. So now, if you look at the left side, it's saying that this here is a function of s. So the variable is s. And if you recall all of the examples we've done, after we've worked out this integral, we're able to get to just a function of s. Yeah? Okay, that's important to keep in mind. Now, here's what I'm going to do next. Next, I'm going to take the derivative of both sides of this equation with respect to s. Since the left side is equal to the right side, taking the derivative of the left side is the same as taking the derivative of the right side. So I'm allowed this. So dds here, and then dds here also. Yeah? Okay, cool. Now, on the left side, I just get capital F prime of s. And on the right side, we're going to move this derivative inside of the integral, but we have to switch to a partial derivative inside of the integral. And what allows us to do that is what's called Leibniz's rule for differentiating the integral. And there's a more generalized rule, but in this specific case, all we'll have to write is the integral from 0 to infinity, and then the partial with respect to s of the inside of the integral, the integrand. So that's e to the negative st times f of t times dt. Yeah? Okay, cool. Now, I'll remind you that partial derivatives treat all other variables as constants. That means that since we're doing the partial with respect to s, that means that f of t is a constant and dt is a constant. So the only thing we'll need to worry about is this quantity e to the negative st. And the derivative of that is negative t times e to the negative st, right? Okay, cool. So that means on our next step, we can write that capital F prime of s is equal to the integral from 0 to infinity, and I will have taken the derivative, so now I have to write negative t times e to the negative st times f of t and then dt, right? Okay, cool. Now I'm just gonna group stuff a little differently on the right side, and this is how 0 to infinity and then e to the negative st and then times, well, I'm going to take out the negative from the t and write it in front of the integral, but otherwise I'll have t times f of t and then dt. Now look here, compare what I have, setting aside the negative sign, compare what I have here to what I had here. The only difference is that t there. So that must mean that without the negative, this right-hand side is the Laplace transform of t times f of t. So finally, we can write that capital F prime of s is equal to negative L of t times f of t. And if you so choose, since all along we're after this guy without the negative sign, you can write as the property is normally written, that L of t times f of t is equal to negative of f prime of s. Yeah? Okay, cool. Now, I already made a recording of this video that was just as good as this one, but I only wrote like f prime of t here, so I botched up the end, and so I re-recorded. Now imagine how much paper I waste. Have a good day.